Hello menu. Hello menu. Menu, can you hear me? Hello menu, can you hear me? You are muting yourself now. I cannot hear you.
Yes, can you hear me now?
Yeah, I can. Okay. Okay, thank you. So you can see my screen, can you?
Yes, I can. Yes, everything's
okay. Lovely, thank you.
Welcome.
Okay. Hello, everyone. Let's start. Before we talk about today's lecture, I would like to remind you about the coursework we have released today and the coming, the second competition. So let me record this session before I forget it.
Recording in progress.
So let's go to your view. As you can see today, we have released the coursework. Okay, so if you click on here, you should be able to see coursework description. Click on this one. It shows you the specification. You have been given 2 data sets. Okay, and there are some tasks you need to finish one by one. And the deadline for you to submit your code is on 30th of April. But some questions related to this coursework will be appearing in the online test part 1. So please do take some time, do this coursework carefully. And this is an individual coursework. Another thing is that tomorrow we will release the second group competition. This time, it's not a mathematical question anymore. It is more related to your Python programming. Many of you, majority of you have already groups have already submitted solutions. For this one, we hope you can also do the same thing. It is about image processing. And the more you actually practice for this one, the more you will be confident for the short term to do your online test part 1. And for the long term, for your career, I would like to say as a data analyst. Okay, this is 2 things I want to draw your attention. Now, let's start today's lecture. Okay, how do we spend our time in this session? Again, 2 parts. First, we visit principal component analysis, and then we have some rest. Then we learn a new algorithm, simple linear regression. First part. By the end of this session, you should understand how the principal component analysis is formulated mathematically, the meaning of outputs of principal component analysis. Okay, so before we start with PCA, let's have a look at some mathematical concepts we need for this session. We have already seen this in our Unit 2. Okay, this is just a gentle reminder. This is the mean for if you are giving a data set. Okay, this imagine the first column, second column, each column is a feature of that data set. So here is the mean of each column. And this one is standard deviation. Basically, this is an average distance between data points to the center of the data. And this is the variance. Variance is basically the square of this standard deviation. Okay. A reminder here. If we know what is this is the covariance matrix. If we know the data has D features, then we know the size of the covariance matrix will be D by D. Now here today, that is something we will use a lot today. Okay. So what is this? Have a look at it here. Do you remember for PCA, what does it mean for this part? Do you remember? Okay. This is the projections. And imagine here this U is a vector, eigenvector. And we project our data, normalize the data onto the principal component, eigenvector. The whole thing here, x multiplied by this vector, is projections. Okay, project our data into PCA space. Now, the variance of our projections is equal to, that is something new today, if you don't know this before, is equal to transpose of this vector multiplied by the covariance of the data matrix, and then multiply by this vector again. Okay, let's have a look at it. This example. Remember this example? We have a toy data set, 2 features, x1, x2, 5 data points. And the covariance matrix of this data set is given here. So the transpose of first principal component is given by here. This is the second one. Here, lambda 1, lambda 2 are the corresponding eigenvalues. What we just seen here, that is the variance. If we have a look at here, remember this one when we talk about principal component analysis. Okay, first the principal component of the data is the vector here, U1, such that projection of the data onto this U1 is given by here. Yeah, this is projections. So let's have a look at it. What is, use this statement. Okay, what do we get? Projections, variance of projections is given by this transpose of U. Transpose of U is given by here, right? That is this part. And then covariance matrix is given by here. That is our second term here. Now, the eigenvector itself, that is transpose of this one, transpose. So we got a column vector here. So I have calculated the whole thing here. So we have 1 by 2, 2 by 2, 2 by 1. So that is the size. What I just said is the size of each vector or matrix here. So from 1 by 2, 2 by 2, 2 by 1, eventually we get one scalar. Okay, the result of this multiplication of these 3 matrices or vectors here is a scalar. After calculation, okay, I got the result for this, the output for this is 16. What is 16 here? 16 for this data set, that is the first eigenvalue. Okay, so the calculation using here variance of projections along the first eigenvector actually is equal to its eigenvalue. Is this a coincidence? Let's have a look at the second one. Now, I want to calculate variance of projections along the second principal component. Second principal component is given by here. Again, I apply this equation here, the statement we have been just seen today, right? So it's given here. The second one, again, multiplied by covariance matrix, multiplied by the second one. One is transpose, one is the vector itself. What do we get? After the calculation, I have got it here. It is equal to 4. It is equal to the second eigenvalue. Okay, so please bear this in mind. What we have already got, we have just obtained is variance of projections along the corresponding eigenvector is in fact equal to the corresponding eigenvalues. So my question is this a coincidence, or is this comes from some theoretical support? Can we have some support? But let's have a look at, okay, just bear this in mind for a moment. Go back to our lecture notes. So this one is the first statement new for today. Okay, variance of projections is given by eigenvectors transpose multiplied by covariance matrix multiplied by vectors. In fact, this is from vector calculus. Okay, we are not going to talk about many other vector calculus knowledge, but today this is something you need to remember. Next one, we have learned derivation with respect to a single variable. Now here today, 3 more, they are vector calculus, okay, again comes from vector calculus with respect to vectors, okay, derivative with respect to vectors. Now, if alpha is a scalar, but here x transpose x itself is a vector, A is a matrix, symmetric matrix. If we do derivative with this x vector, what do we get? We get 2ax. With respect to x, we can consider this A is a, doesn't matter it's a matrix or what, we consider it as a constant, right? And the 2x transpose multiplied by another x, loosely speaking, just imagine this is x to the power of 2. So when you do derivative with respect to x, you got 2x. That is what we have here. Similarly to here, beta is a scalar. Okay, x again is a d by 1 vector. It's a column vector. One column, but d rows. With respect to x, what we get is 2x. Loosely speaking, just to consider here is x to the power of 2. With respect to x, when you do derivative, we get 2x. Now here, if we have, okay, x transpose of x multiplied by a constant, this is equal to, if we transpose to a and then multiply by the vector itself, with respect to derivative, with respect to x, we got this, the constant a. These three are new to okay. Now, have a look at here. I don't think we provide you these statements so in previous lectures. However, we have already used this one. Okay. Now have a look at here. The transpose of a product of two matrices is given by equal to leftmost transpose. Similarly, we can do the transpose for the product of three matrices. It is equal to rightmost transpose multiplied by the middle one transpose multiplied by the left one transpose. Do you remember in which lecture, which topic have we used this? How about this one? When you are given a matrix M, we do singular value decomposition. A matrix can be decomposed into parts, right? And now, I think in that lecture, we gave you the results directly. So if we know the transpose of this M, then we should know the transpose of this M, okay? Which three parts we can get. So how do we get this? That is what we have already applied for. So M can be decomposed into three parts. These three parts are transposed. Then the rightmost, that is here, write it first, write it down here. The second one is transposed. The leftmost is transposed. Now have a look at here. Transpose to itself, and then transpose again, we get the original V. Because here S is a diagonal matrix. Remember singular matrix. This one here is a diagonal one. So elements of the main diagonal line, they are zeros. So the transpose itself is equal to the original one. And then here is UT. We just copy down here. That is why we have how we get this. Okay. Some preparation. Okay, so far what we have learned, this one, variance of the projections is given by here. That is the vector transpose multiplied by the covariance matrix multiplied by the vector itself. And then 3 derivative with respect to vectors. Finally, is transpose for the product of matrices. Now, you have already learned the basic idea about PCA, right? We mentioned what is the aim for PCA? Extract the most important information from the data, but we haven't detailed, give you more information about what is, unearth about this most important information. How did we, get this part? We will talk about it very soon. And what we can do using PCA, compress the size of the data set by keeping only this important information. We can visualize the structure of data. So, for example, like here, the teapot is our data. Okay, the aim is to use PCA. Hopefully, you can see the overall, the whole picture of the PCA, not just a part of, but the whole shape of the PCA. So, for example, here, remember, in the pre-recorded video for Unit 1, we talk about Iris flower dataset. 150 data points, 4 attributes, 3 classes. If we do PCA on it, that is what we get. Here, x-axis and the y-axis, they are not one of these features. What are they? They are principal component, first principal component, second principal component, and each component here is a linear combination for all these features. It's not easy to see the idea behind the PCA from this figure because, we have more than 2 features here. That is why when we talk about PCA, we give you this simple toy data set. 2 columns, x1, x2. This is just a scatter plot for PCA. Here is the PCA plot after we do PCA. What's the difference? As you can see, we mentioned earlier, right, in our Unit 2. So it seems like we have somehow rotated the data points. That is, in this new PCA in this, among these data points. Yes. So we rotate data so that the first of the main axis now is, sorry about this, I don't know what happened. Yeah. So along these distances, the largest distance has been captured. And then the second axis actually is perpendicular to the first one. That is what we learned in Unit 2. In Unit 2, when we talk about PCA. And we were talking about how can we find a new coordinate system that can capture the distances in the data set and also can give us a perpendicular coordinate system, each axis perpendicular to each other, right? So back to here. Definition. The first principal component of the data set is the eigenvector we mentioned earlier, is the vector U1, such that projection of the data onto U1 is given by here. That has the largest variance, the distance among the data, and subject to the normalizing constant. Does it sound familiar? Maximize something under a certain constraint. What did you learn on last Friday's lecture? Have you learned optimization with constraints? Okay, now can you write down what the objective function could be with the constraint you can use? Just based on this sentence. That is, okay, how would you like formulate it using mathematical equations? How about this? Yeah, the variance of the projections along the first principle, along the U1 now, because we don't know, we try to formalize the problem, okay, using mathematical equations, and then we try to project the data onto a vector so that the variance along this vector is maximized under some constraints. What is these constraints? Constraints is that all vectors should be perpendicular to each other. If now we consider only the first one should be a unit vector. So, okay, that is what you have already learned on last Friday. Right? We introduce to solve a problem, optimization problem with constraints, we need to introduce Lagrange Multiplier, right? So we have a cost function, error function, objective function, you can call it, yes? And we have a constraint function. By introduce this Lagrange multiplier, we can rewrite our objective function. That is original one minus multiplier is two terms. Okay, here I only mentioned minimize, but actually this method can be used for both maximize and minimize. How can you tell when a point that satisfies the conditions really is a constraint maximum or minimum? The answer is that it depends on the constraint function here and together with any implicit constraints. So really it depends on the application. But you should bear this in mind, this method can be used for both minimize and maximize. Okay, once we fixed this objective function, then what do? You calculate the partial derivative with respect to variables and Lagrange multiplier. Okay, and then to calculate the variable values and lambda here. Okay, so I think I passed it. Okay, they are here, sorry. Okay, here. So here, that is the finally formulated objective function. Our aim is to maximize here. What is this? This is what we just talked about, variance of projections. Yeah. So constraint is here. The vectors, we are trying to find new vectors, new coordinate system. The first vector is, must satisfy this constraint. It is a unit vector. Okay. When we rewrite this objective function, what do we do? Using the original objective function minus this lambda, that is Lagrange multiplier, and then here we write this in this way. Yeah, this is a constraint function. Now we need to calculate partial derivative. What is this? Can you do it now? Or maybe with me, but please use your pen and notebook. Let's have a look at it together. Okay, this is our new objective function. Our aim is to calculate partial derivative with respect to this u1. So u1 here and the sigma here, I have underlined here to denote they are either vectors or matrix. Remember here, today we have just learned, if we want to calculate partial derivative with respect to this vector, we use this one here. So it gives us 2ax. X is, in our problem, that is our u1, and a, that is our sigma. So for this first part, after apply this one, that is what we get, 2 sigma and then u1. Have a look at the second term here. With respect to u1, lambda 1 here is a constant. So what is, partial derivative with respect to u1 here? Let's have a look at which one we should use. The second one, beta 1, this one. Okay, so it should give us 2 rather than x, we have u1 here. So I write it down like this. Lambda 1 is a constant. I copy it in front of this 2u1. And then I rearrange it. That is the final result. Have a look at back here. Now, I have already shown you through our whiteboard notes. Okay, that is, this part is what we have got. Remember, when we learned that optimization with constraints, right? We introduce this Lagrange multiplier, and then what? After we calculate this partial derivative, we set this equation equal to 0. Remember, the aim is for us to calculate what is this u1. What is this u1? We set it equal to 0. That is what we get here. Yeah, that is what we get. Further from here, what do we get? We can get here. What is this? Right? We can get here because we can cancel 2 at both sides. And then this gives us this equation. What is this? What is this? If you think back, the definition for Eigen Decomposition, when we have a matrix, a square matrix, and if we get a lambda is a real value, and the corresponding eigenvector basically is a vector. If we can get a value and a vector such that we can get an equation like this, then this is our Eigen Decomposition. Now, look back again. This sigma is the data's covariance matrix. It's a symmetric matrix. And this U1 is what we are looking for. We want to find a vector such that this is a unit vector. The length of this vector is equal to 1, and this vector should be also perpendicular to other vectors. Okay, but this, for this given covariance matrix, it says we can find a U1, we can find a lambda 1 such that this is equal, is valid. Now, come back to the original idea. To formulate PCA, the aim is to find a vector such that projections along that vector has the largest variance. Now, this one, at the beginning when we do the preparation, this one is equal to, you have known, is equal to this vector's transpose multiplied by covariance matrix multiplied by this vector itself. It can be written, use sigma to denote covariance matrix. Now, because we got this equation here, so we can rewrite this part, sigma U1, as lambda 1 and U1. Okay, so how did I come from here to here? That is because I substitute this part into here. That is how I get here. Now, because this lambda 1 is a constant, I can take this lambda 1 in front of vector. Take it into, in front of this vector. So I rewrite this like this. Remember, we have one constraint. The constraint is that U1 is a unit vector. So that is why the whole thing here now is equal to lambda 1, because under this constraint, U1 is a unit vector. So now we can confidently answer the question I asked you earlier, right? The variance of projection, we empirically actually proved when we calculate based on this matrix vector multiply the covariance matrix, the output, we actually empirically proved the variance of projections along a specific vector, in fact, is equal to the eigenvalue for that corresponding eigenvector. Okay, so what we have done here, just because we have many equations here, let's do it slowly so that you can follow. The aim, we mentioned the goal for PCA. Sorry, go back to here. For PCA here, is we are looking for a new coordinate system such that along the first vectors, along the first vector, it can capture the largest variance in the data set. Okay, it seems like, how did we do that? We first define how should we formulate this variance mathematically. That is what we have done here. How do we formulate it? Basically, it's just the variance of this. Now, variance of this is given by this vector's transpose multiplied the covariance of this part multiplied by this vector. And then we do optimization with constraints. Optimization, that is, we are trying to optimize this part. This is the variance of projections subject to here. Then follow what you have learned last week. Introduce multiplier, Lagrange multiplier. get the new objective function. Then calculate partial derivative with respect to what do we want to get? We want to get what is this vector. Okay, with respect to this vector, then we get here. Okay, so it says as long as we can find a vector of the, for this one, if we project our data along this vector, then we should get the largest variance along this vector. And that largest variance actually is given by this eigenvalue. That is a different way to think about PCA. Now let's have a look at next step. This is just for the first principal component. Have a look at for the second one. The second one, similarly, we want to along the second direction eigenvector or principal component. We get the second largest variance. This time, the constraints include 2. Again, eigenvector should be a unit vector. The length of the vector should be equal to 1. And it should be right angle perpendicular to the first one. So now, when we calculate objective function, we write objective function. This is the original objective. And then we have 2 constraints. One is followed here, unit vector. The other one is here. We have they are perpendicular to each other. This time we have 2 Lagrange multipliers. What about this time? We do partial derivative with respect to the new vector u2. What do we get? So I'm not going to repeat this part exactly the same like what we have gone through for the first eigenvector. But we need to pay attention to here. What do we get? With respect to u2, we can consider rho and u1. This is because this is a partial derivative. We can consider this rho and u1 as constant. So when we calculate derivative with respect to u2 for this part, we basically just get rho multiplied by this u1. They are constant. Now have a look at here. Okay. We have already written in the previous slides. But here, this one is the result. Okay, so the first 2 terms are the same as if you see how we calculate with respect to u1, right? Now we have one more term that is for this part. So this is the partial derivative with respect to the second vector. Now we need a little bit patient. Okay, we need to be patient to see the final result for second eigenvector because now we have one more constraint. So after we get partial derivative, again we set the whole thing equal to 0. Okay, what does it give us? It's not that obviously to be seen. So what I did, we multiply a new vector, u1 transpose, at both sides. When we multiply a vector, we write this vector in front of other vectors. So here we have 2 multiplied by transpose of u1, 2, that is here. The second term, we do the same thing. We write this u1 transpose in front of this vector. Similarly to the third term, multiplied by u1 transpose in front of u1. What do we get? Bear this in mind, okay? What in mind? What here constraints. So, what do we have now? How can we get from here? That is what we have for this part. okay, to here. Let's think about it. Because U2 and U1, they are perpendicular to each other, so this term is 0. Okay, that is comes from here. Okay, so transpose of U2 to U1 or transpose U1 to multiply by U2 is equal, okay? The point is they are perpendicular to each other, so the dot product of these two vectors are 0. So we don't have this middle term anymore. And for this term, because this is a unit vector, so this term here, U1 transpose to multiply by U1 is 1. So that is why we got rho here. So that is why the first term here is equal to rho. If we, move this, remove rho, minus rho to the side of here, this side. So that is what we get. Okay, now continually. That is what we have already got so far from the previous slides. Okay, for the previous slides, we stopped at here. Continually. Okay, now from the first eigenvector, that is what we have. So be careful with the index, subscript, for each vector here. That is what we get. If we multiply U2 transpose at both sides of here, what do we get? I said earlier, if that is a vector, when we multiply by it, we put it in front of matrix of vectors. So at both sides multiplied by here, that is, I write this one in front of this term. Similarly, multiply by this one to this side in front of everything, like here. Why do I have equal to 0? Because, now have a look at this term. What is this? This is saying these two from this constraint here. These two vectors, they are perpendicular to each other. So that's why we have 0. So this gives us, from here. Okay, we multiply by U2 transpose. We got it to here. So this part now tell us equal to 0. So how can we make connection from here to what we have already got in previous slide? That is here. Remember the transpose of product of matrices here. So this one that is here, if I do transpose, what do I have? The rightmost transpose first, write it down here. Middle part transpose, because this is a symmetric, transpose itself is still itself. So we have here U2 transpose again, we get U2 back. So you see, this part is here, right? Because here it's 0, so the transpose of it is also 0. That means this part is 0. So that is why we get here rho is equal to 0. Now, have a look at here. If rho is equal to, this 2-star equation here. If rho is equal to 0, okay, then we don't have this term anymore. Subtract these two terms, the first two terms give us 0. That means the first two terms, they are equal. So that is why we get here. So what is this? This is again another Eigen decomposition. Okay, so if we continue to calculate variance projection or project our data along the second eigenvector, what do we get? Okay, from the preparation on the beginning, variance that is belongs to vector calculus. Okay, so it gives us, it should be equal to vectors transpose multiplied covariance matrix multiplied by the vector itself. Now we know this term is equal to here. Yes? Because lambda 2 is a scalar, a constant, we can bring it in front of this vector. We rearrange this term and write it down like this. Now, here, this part is a unit vector. Is one of our constraints here. So that is why, again, it shows us answered our question on the very beginning here. Remember here for the second one. Why is this coincidence? It's not. It is well supported by what we have already proved here. Okay, so we won't do it for other eigenvectors. Let's just stop here and summarize what we have just done. We have formulated idea of the PCA mathematically. We tried to project the data into a new coordinate system. Along the first axis of the new coordinate system, data should has the largest variance. Along the second axis of the new coordinate system, data has the second largest variance. And the second axis should be perpendicular to the first axis. We have found when we compute the vectors using Lagrange method, each vector is in fact the eigenvector of the covariance matrix. I hope you all agree with me. We take some time, go through this. In this module, we are not going to teach you many different algorithms, but we instead focus on two simple algorithms widely used in machine learning or data analysis. One is principal component analysis. One is simple linear regression. So I hope the way we teach you for PCA can show you how you can use what you have learned so far, linear algebra, calculus, to formulate a mathematical to formulate a questions mathematically. So in this way, I hope it can help you to read more research papers and understand more algorithms on your own. That is something we have already talked about it. After doing Eigen Decomposition, how do we know which one is the first principal component, which one is the second? We actually sort the eigenvalues. The largest one corresponding to the eigenvector, that eigenvector would be the first principal component, right? Now, I hope this makes sense to you. Why it is so important for everyone when you get a principal component analysis done, you should always report how much variance has been captured in each, if you plot a projection plot in each plot. Because, why is that is important? Because each principal component actually measures, the eigenvalue variance along that direction, the variance of projections in that direction. Okay, so this is why if you haven't received any training, you just apply a toolbox using PCA. You may just show a plot there. However, after you received the training, okay, we show you why, what does it mean this lambda, why this is important. Now, whenever you generate a PCA plot, you should always bear this important information, or bear this in mind. You should always report how much variance has been captured by that figure you show in your report. Okay, if you plot, say, the first against the second, you should plot, okay, what is the first eigenvalue plus second eigenvalue against, the total variance. If you plot the third against the fourth, then what is the third plus the fourth, and then against the total variance? You should always report it. Okay. Now, this is something about a PCA. In practice, we have already seen this one before. Now, because you have already tried PCA using both sklearn and your own step-by-step code, so calculate covariance matrix, do Eigen Decomposition, and you see this is the step. I think this shouldn't be too difficult for you now. What I want to emphasize before we finish this session is here. Square plot. We mentioned a little bit about this square plot in Unit 2. A square plot displays the eigenvalues in a downward curve. It orders eigenvalues from largest to the smallest. Okay, so here I want to draw your attention here, component number. Can I ask you a question? What do I mean by component here? So if I say the Irish data here, four features here. When I say component numbers here, what do I mean? Do I mean four features there, or do I mean what? Principal component. Or let me ask you another question. When we say we can use PCA to do feature extraction, after you do feature extraction, each feature is it a feature from the original feature set, or is it a feature from principal component? Okay. Have a look at here. Back to this simple data set. Two original features here. After I do projections, that is, I get a first principal component. Projections on this data set, on this plot, that is given by the original data multiplied by eigenvector here. Okay, so let's consider only the first row, the first data point, multiplied by, basically I project the first data onto the first eigenvector. That is what I have. So have a look at the calculation here. So -2, that is the value for x1. x2, that is the value for x2. So the projection for this first principal component involves information from both original features. My point is, when we say we do feature extraction using PCA, quite often students made a mistake saying, oh, I want to select, for example, here, select 3 features. Oh, those 3 features actually come from the original feature set. That is wrong. That is wrong. All it says, okay, here, I got 3 features now. I got the first 3 principal component features. Each of these principal component features, in fact, is a linear combination of all original features. That is the last thing I want to emphasize for this session. Now, as usual, no surprise, I'm late again. Let's have about 10 minutes rest. Come back at 4:05. Okay? Let me stop.